When you see an AI write an essay or generate some wild image or translate languages in a split second, have you ever stopped to wonder how it all works? Well, believe it or not, most of it can be traced back to a single, solitary research paper from 2017. And today, we're going to break down exactly how that paper completely changed the world.
So it all started right here. Not with some massive, flashy product launch, but with this. A deceptively simple, 8-page academic paper. The title was Attention is All You Need. It was written by a team of 8 researchers over at Google, and at first glance, it just looked like a pretty clever improvement in machine translation. But here's the thing. It wasn't just an improvement. This paper laid out the architectural blueprint for pretty much every major AI system we use today. We're talking ChatGPT, Gemini, DALL-E, the whole shebang. So the big question is, how? How did this one paper do all of that? Okay, let's dive in. To really get why this paper was such a lightning strike, we need to understand the world before it. We need to look at the biggest problem AI was facing with language, which was this thing called sequence transduction.
Now, that's just a fancy academic way of saying you're turning one sequence of things, like an English sentence, into another sequence, like its German translation. The problem is, language is tricky, right? The meaning of a single word can completely change based on all the other words around it. Context is everything.
Back then, the main tools for this job were called Recurrent Neural Networks, or RNNs for short. And they worked by reading a sentence one word at a time, in order. And this created 2 massive problems. First, it was painfully slow because you couldn't process anything in parallel. And second, the model had a terrible memory. It would tend to forget the beginning of a long sentence by the time it got to the end.
I love this analogy. Imagine trying to summarize an entire chapter of a book, but you can only use a single tiny index card. And you have to keep erasing and rewriting your notes as you read each new word. You'd absolutely lose all the important details from the first few pages, right? Well, that's exactly what was happening inside these AI models. So this is where the 2017 paper just blew the doors off. The researchers looked at this whole one word at a time bottleneck and proposed something, well, truly radical. See, they'd been using a mechanism called attention as kind of a patch, a little helper on top of RNNs. But then they asked a totally different question. What if we just threw out the RNN part entirely? And this is the absolute key. The paper's title wasn't just some catchy phrase, it was a bold technical thesis. They were literally arguing that you could get rid of the slow, sequential part of the model and build a whole new architecture based only on this attention mechanism. And they called this new architecture the transformer. It was designed from the ground up to understand the relationships between all the words in a sentence at the exact same time, which completely eliminated the need to process them one by one. Okay, so how does this magic actually work? Let's pop the hood and take a look inside the engine that drove the entire AI revolution. All right, so this is the famous diagram they proposed. It looks super complex, I know, but it really breaks down into 2 main jobs. You've got the encoder over on the left, which reads the input sentence and just tries to understand its meaning. Then you've got the decoder on the right, which takes that meaning and generates the output sentence. And the real magic, the secret sauce, is what's happening inside those blocks labeled multi-head attention. Probably the best way to wrap your head around attention is to think of it like a database lookup or a search engine. For every single word, the model creates 3 things: a query, a key, and a value. The query is like the word asking, hey, who in this sentence is important to me? It then compares its query to the key of every other word to find a match. Once it finds the words that are relevant, it pulls their values. Let's just walk through this real quick. So for any word, its query gets compared against every other word's key, and that generates a relevant score. Then those scores get scaled down a bit just to make them easier for the computer to handle. After that, they get turned into weights, which are basically just percentages of importance. And finally, these weights are used to create a brand new version of our original word, one that's now blended with all the information from the other words it just paid attention to. But the transformer doesn't just do this once. Nope. The paper introduced what they called multi-head attention, which means it runs this whole process in parallel a bunch of times. In the original paper, it was 8 different times. So why do this? What's the point? Well, this analogy explains it perfectly. Each attention head is like a different specialist. It learns to look for different kinds of relationships. So one head might focus on grammar, while another tracks what a pronoun is referring to. And by combining all of these different views, the model gets a much, much richer and more complete understanding of the text.
Okay, but there was one big problem left to solve. If you're looking at all the words at the same time, how in the world do you know what order they're in? The cat sat on the mat is very different from the mat sat on the cat. The solution was just mathematically beautiful. They created a unique positional encoding for each spot in the sentence using a clever mix of sine and cosine waves. This gives every single word a unique little mathematical timestamp, letting the model understand the order without having to read one by one.
So the architecture was brilliant, no doubt. But did it actually work? Well, the impact was immediate, and it was absolutely overwhelming. This simple little table from the paper shows you the entire revolution in a nutshell. An old-school RNN needed to take n steps to read a sentence that was n words long. But with self-attention, the path length between any two words is just 1. This was the key. This meant you could process all the words at once, which unlocked the insane parallel processing power of modern GPUs. And suddenly you could train these models on way more data than anyone ever imagined. That changed everything. The results were just stunning. On the standard benchmark for English to German translation, the transformer hit what's known as a BLU score of 28.4. Now, that number might not mean much to you on its own, but in the world of AI research, it was an earthquake. This was a 2-point jump over the previous best model, which, by the way, was an ensemble, a whole team of models all working together. A single transformer didn't just match the competition, it blew right past them. And what happened next is basically AI history. In 2018, Google's BERT used the Transformers encoder to completely change how search works. Then OpenAI's GPT series used the decoder to create these incredibly powerful language models. By 2022, ChatGPT brought this technology to hundreds of millions of people. And today, this exact architecture is the foundation for almost every major AI system you can think of. And it all comes back to this one little equation from page 4 of the paper. It might look simple, but this right here, this is the mathematical heart of the attention mechanism. It's the formula that now powers a multi-trillion-dollar industry and is literally reshaping our world as we speak. The transformer proved that a simple, scalable idea could unlock an unbelievable amount of intelligence. That single idea was the spark that lit the fuse. And the question it leaves us with is, what's going to be the next one?